Hi, everyone. I'm new. I'm here to help out the other hosts. I hope you're enjoying the conference so far. My name is Sri Ram Ramakrishna. People call me Sri. With that intro out of the way, I will introduce our next speaker who will be doing a lightning talk. In fact, we'll have a couple lightning talks in the schedule. So to kick that off, we'll have Yusheng Sai, who will be talking about Ginkgo's SYCL backend and its integration into nekRS. Over to you, Yusheng.
Thanks for kind introduction. Yes, so today I will show how we develop the Ginkgo SYCL backend and provides the integration into the nekRS. So first, our target application is nekRS. So nekRS is quite famous and popular in the HPC application. His targets like the fast and scalable CFD simulation. And currently, nekRS is rely on the OCA portability layer to enable hardware portability. And in the bottom, you can see some of the animation from the turbulence pipe here. And then it's need to run several times, and then it needs a good solver to solve this turbulence simulation here. So as the Ginkgo team, we would like to provide another option in nekRS. So nekRS currently use OCA, or they can use MGX from NVIDIA, or like the Hyper from National Lab, and to solve the cost grid problem. And Ginkgo side, we previously showed successful integration for Sandia, MFAN, OpenFOAM, or many applications. So in this talk, we would like also to bring the Ginkgo into the nekRS. So why is the portability is important nowadays? So if you check the top 500 lists in the website, so except from the fourth supercomputer, the Fugaku use the ARM system, and then all supercomputer in the top 6, they all equipped with the GPU, and also it's from different vendor from NVIDIA, AMD, and also from Intel GPU. And then if we use another example, so here is the performance share from the top 500. So it's an entire here, and firstly, the laptop with the black box is only CPU, and on the right side, the red box here is use the AMD as the accelerator, and then the blue box use the Intel GPU as the accelerator, and then the rest use the NVIDIA GPU as the accelerator. So for now, if some software only supports once, you will maybe lose half or 1/3 of the supercomputer resource in the world. So sometimes you want to support more vendor, and then you can easily to shift from one vendor to another vendor, and then fit more hardware easy. However, the portability is not easy. So usually to overcome this portability challenge, we can go for like the portable language, or we can also use native language to handle it. So for portable language, we like the nekRS, they use the OCA, or some library use the Cocos, or like the OpenCL, or OpenMP, or SYCL here. So the benefit here is you use portable language, you just need to maintain one code base. Definitely it's less maintenance, but it's on top of the native language, so you always have another abstract layer, and definitely you have some performance impact, because they either usually they provide the subset, like the interaction here, so you only get some benefit from the vendor library here. And another way is you use the native language here. For example, you use CUDA for NVIDIA GPU, and HIP for AMD GPU, and SYCL for Intel GPU. You definitely get the latest feature, because this compiler and this ecosystem supported by vendor directly, and you should get the best performance here. But you will encounter, if you want to support all in one place, you need to maintain different code base. And when you read the documentation, you also face some different technical term inside the documentation, and then you need to figure out what kind of fits your needs, and you can tilt your performance for different hardware here. So to nekRS use the OCA, so they already when OCA supports the Intel GPU or AMD GPU now, they can easily shift there. But Ginkgo use the different way, so we use the native language to support different backend. But to ensure our sustainability, first we have the design to ensure the sustainability and the portability in the mind. So first we have the code to get some infrastructure algorithm. So it's somehow you write your pseudo code for iterative solver or for the preconditioner, but it requires some backend to support the real operation. So first we use a reference. It's only like a single thread, and then we try to write the kernel in a simple way or in a stupid way to make sure we can easily verify it's correct by the Google test here. And we use the SYCL to ensure each commit is past the pipeline here. And then move to the different backend. Like we have multi-core CPU, we use the OpenP, and we write the CUDA kernel for NVIDIA GPU, write heap kernel for AMD GPU, and use the DPC purpose or SYCL nowadays for Intel GPU. And to ensure the correctness, we always have the test to compare the result from the accelerator and the single thread reference kernel here to ensure everything is correct up to some numerical error aspect here. So for now, we provide the entire library focused on the sparse linear algebra solver here. For now, we have the nekRS, we use the OCA, and then they can support widely device. And we also have the Ginkgo supports widely device now. So we try to put that together again. So for now, we put the Ginkgo into the nekRS. So what's the role in nekRS? So nekRS already have their own geometric multi-grid digitization, so they will not form the matrix directly, but in the code solver, they will form the matrix, assemble the matrix explicitly. So we can take it as the CSR sparse matrix into the Ginkgo, and then we solve it by the Ginkgo, and then we return the result back to the nekRS, and then use this to do the following multi-grid step here. So first, we definitely keep the portability, and then we also bring many solver, which is not really exist in the nekRS itself. Definitely from the basics, we need to support the sparse matrix operation like the SPMB or SPM, and then we provide pretty decent amounts of the quite a lot of solvers like by CG, by C-step, or CG or GMS, and they both, and also the precondition is some like you can image like the dark Jacobi or incomplete LU and here, and then we also have some fancy batch solver. It's not used in the nekRS. And also we support the algebra multi-grid, which is designed in nekRS currently. And most of them are supported in the distributed fashion, so that we can still use it in the scalability test from the nekRS. Yeah. So with the Ginkgo, we definitely want to make sure it's easy for use. So inside the nekRS config, you just need to measure out which solver you want here. So for example, like the pressure, we just need to mention like code solver use the Ginkgo, and then Ginkgo can identify which config they need to use. And from the user side or like from the developer side, we have so many options. So sometimes this problem might require the conjugate gradient, and the other problem requires the algebra multi-grid. We can simply swap them. So how that looks like in the config file here now. So on the left side is we configure a conjugate gradient, and then you can run up to 4 iterations, and then you have some certain threshold for the residual. And on the right hand side, we can configure the AMG, the algebra multi-grid here, and then you can configure which kind of the cosine method you want and how many iterations you want here. And after you configure this config file, and when the application or like developer want to test, they just need to, I need CG, I just paste the CG file paste, and then also they can switch to the AMG or like furthermore like a GMRS or different solver combination. We can simply to test different options and then to pick up the good one to the user for them use. So after that, we would like to show our portability. So we have given a talk about these results in the past CFD, but I only captured like 1 or 2 slides here because I don't want to destroy accession from the Intel GPU now. So on the left side is we run some small examples. So it's the Goblins example and use 16 discretization point per dimension on our self-host AMD MI100 server, and it's runnable, and then we can see some scaling benefit here. And on the right hand side, we have more proper server on URIC Research Center, and then we run on a larger problem, like we use the 128 discretization point per dimension NVIDIA A100 server. So each node have the 4 GPU. So we run different rank here, and then until we use the 110 nodes. So in total, we have 440 GPUs now. And it's already shown when we use the Ginkgo CG in this program, we can get 1.1 speed up here on this system. And then we go into the Intel GPU. So nekRS supports Intel GPU in the next release. Unfortunately, it's still work in progress. So there are some unstable currently, and we still based on this work in progress release. And so hopefully we will get the stable release in the end in the next release. And we run 3 example from the nekRS the SYCL here, and then currently we only consider 2 options, so smoother from the nekRS and conjugate gradient solver from the Ginkgo. And then to ensure we get the stable timing, so we run more than 3,100 steps, and then we only take the time from 3,000 steps to the 3,100 steps here. And from this example, we have 3 options, and then unfortunately we can only run on 2, up to 4 nodes now. So entirely we have the 32 GPU tile, and then we can see some difference. So in the bottom is with the dash line is always the from the smoother, the OCA smoother from the nekRS, and the solid line is from Ginkgo, and then different marker meaning different example here. So in some in Gopher is pretty small problems, the smoother is faster than the Ginkgo CG. And then, but in the RBC example, in the beginning, Ginkgo CG is slower than the smoother here, but we have better scaling effect. So after we double the nodes, we get better performance than the nekRS smoother. In the top ones, we always faster than the smoother, and then the Ginkgo CG reach out like the 1.4 speed up here. So in the end, we just show like quite preliminary results on multiple GPU. It's maybe a bit tiny toy example. So from combined with the previous result, we show the experiment also on different method to show the portability we have now. And so Ginkgo keeps this portability from the nekRS and also overcomes this diverse accelerator nowadays, and we bring more solver option to nekRS so that they don't face any issue. It's currently based on the work in progress, so we will definitely need to continue this work on the large experiment after the stable release. Thank you.